Am I started? Hi guys, it's Dr. Foy. I am going to give you a screencast. I'm going to talk about Chapter 10 and I'm going to introduce the first concept in Chapter 10, okay? And then on Monday, when we get back, we'll move on and talk about the rest of the chapter. So, this first chapter is valence shell electron pair repulsion theory, okay? Electrons don't like to be close to one another, okay? Electron pairs, we've gone through this whole thing about, how we build up the electronic structure and, why they don't pair up until they absolutely have to. Okay, now we're talking about pairs of electrons, and they don't want to be close to one another, so this is why it's called repulsion theory. So they're going to orient themselves as far apart as possible, okay? So if you think about a central atom, and this all goes to the central atom, okay? So we're only talking about the geometry around the central atom. You got three things surrounding a central atom, and if you think about the geometry of that, the furthest apart you can get is in this triangular pattern, and it's actually called trigonal planar, because if you, again, think geometrically, if you try to move any one of those three groups out of the plane, it actually gets closer together. Okay. So the first thing we're going to look at is linear geometry. Pretty straightforward, right? You have two things attached to a central atom, something like this BeCl2 or this CO2, 180-degree angles for the bonds from one bond to the other. Okay. That's the geometry that any linear structure is going to take. Okay. Now we're going to move on to trigonal planar geometry. That was actually the first thing that we looked at. The bond angle is 120 degrees. Okay, so we're taking Lewis dot theory, right, which we talked about on Tuesday, and we're taking that and we're building these molecules first, and now we're going into the geometry surrounding that. So here's trigonal planar, right? The bond angle is 120 degrees. Again, try to move any of those fluorines off the BF3, and it's going to end up being closer than 120 degrees. All right. So another depiction of this trigonal planar. The next one is with four things attached. Okay, so you've got four bonded items around a central atom, and that's going to result in what we call tetrahedral geometry. And here's what that looks like in a second. Here it comes up. Okay, so we've got this tetrahedral geometry, bond angles about 109.5 degrees. All right, again, this is all emphasizing how far apart can these electron pairs get from one another. Okay, here's another view of the tetrahedral. Moving on to trigonal bipyramidal, because this is the next in line. So we got five things attached, okay? And this one's actually a little more interesting. This trigonal bipyramidal means that we've got different positions. So we have something called an axial position and an equatorial position. The equatorial position is the triangle. The bipyramid is the axial positions, okay? And those are different positions. Okay, so if you look at this depiction of it, right, you've got the one on the top and the one on the bottom. Those are in the axial positions, and then you've got the ones on the equatorial plane or the triangular plane there. The angles are different, so they're 120 degrees in the equatorial positions and 90 degrees CO2 equatorial position. All right. Okay, here's another depiction of that. All right, again, you've got the two axial, and then you've got the three equatorial. All right. And another picture of them. The next one we move to is octahedral geometry. So octahedral is when you have six things now attached to that central atom. All right. It's actually it's an octahedron because it has 8 sides. But as we look at this thing, right, we've got the 4 on what we were calling maybe the equatorial, and then if you look at that, we've got 4 on the axial and 4 on the other axial. So that octahedral geometry is, they're all equivalent, right? It's basically a bunch of squares here put together. And so all those angles are 90 degrees. Okay, another depiction of that, right, with the fluorines. Again, you look at any one of those planes, you cut right down through it, and you've got square, 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 square everywhere. All right? All right, the last view there. Okay, so now that is when everybody, okay, that's when you have all bonded pairs of electrons. Lone pairs are electrons that are not part of the bonding, right? We looked at those again in Lewis dot theory, and we got lone pairs around the central atom. And when you have those lone pairs, they affect the geometry. The way that they affect the geometry is not by being seen, right? Because you can't see the electrons. You can see the bond, you can see the result of the bond, right, where the atom lies. But this lone pair actually takes up space, okay? They're electron pairs, and so again, valence shell electron pair repulsion means get away from me. But these lone pairs don't have another nucleus pulling on them, and so they end up being bigger, and they end up affecting the geometry, okay? So in this case, this isn't a lone pair situation, but this is more electron density with a double bond, and so the effect is you don't have 120 degree angles, but you have 121.9 between that oxygen and the hydrogen, because that double bond is pushing things away because there's another pair of electrons in there. Okay, but lone pairs actually occupy even more space. All right, so sorry, advanced way too many times. This is a little slow. Okay, so you've got this lone pair. That is going to be the largest size, right? The lone pair bonding pair is a little bit smaller, and then bonding pair. So again, this affects the angles. So think about this one. Here's NH3, right? If we had all 4 sites occupied, that would be tetrahedral geometry, but we don't. One of those sites has a lone pair on it, and so it depresses the angle on all the other hydrogens there, okay? So that hydrogen, nitrogen, hydrogen, right, is the angle we're talking about. 3 points determine an angle, and so that is less than the 109.5 because, again, look at how big they're showing that lone pair, right? It's making quite a difference. Here's something that is near and dear to our hearts: water. Water, if, again, there were 4 things bonded to oxygen, it would be tetrahedral geometry. Take away bonded and put lone pairs in there, and it has a dramatic effect. It goes from 109.5 down to 104.5, okay? And that is this lone pair effect. It's a distortion of those angles. All right? So let's take a look at how this affects trigonal planar. Okay? So if we start with trigonal planar and we remove one of those bonded atoms, right? In trigonal planar you have 3 bonded atoms. Remove one and replace it by a lone pair. So now that sulfur has a lone pair on it. What it does is it depresses the angle. Now this is what I want you to recognize. That angle is less than 120 degrees. I don't care that you know that it's 119, 118, whatever that angle is. I just want you to know that it's less than 120 degrees. Okay. Here we've got the tetrahedral and the pyramidal shapes that come from the tetrahedral. So we looked at that NH3, right? And there was a lone pair there, and you got what's called a pyramidal shape, right? And so there were the 3 legs, the hydrogens, and then there was the lone pair on the top of the nitrogen. That's a pyramidal. Then you take off one more, and we were to water, and we had that bent shape that came out of removing again another one of those bonded atoms and replacing it with a lone pair. So you had two lone pairs and two bonded. Again, it went to this bent shape that was less than 109.5. Same thing with the pyramidal, less than 109.5. All right, so this is a trigonal pyramidal shape. Okay. All right. Moving on. Let's look first. So here you have the tetrahedral geometry. Here we have removal of one, and now we've got a lone pair there. That pyramidal, that trigonal pyramidal shape, again less than 109.5. Another pyramidal shape, less than 109.5, and then the bent shape from water, less than 109.5. Okay, another depiction of the bent shape. Okay, so now we move on to the trigonal bipyramidal. Okay, and the first one, this is where you have to make sure that you're removing the correct position. Okay, so remember the trigonal pyramidal had the equatorial and the axial. So we always remove from that equatorial position first. Once you remove the equatorial, you remove one of them and it begins to look like a seesaw. So we call that the seesaw shape. You remove a second one and now you have a T shape, and you remove a third one and now you've got a linear shape, okay, because all you've got left are the two axials. Okay, so going through them, here we remove again the equatorial position, and if you throw this thing on its side, you'll get something that looks like a seesaw. Alright, there's the seesaw shape again, moving it to its side, bam. Alright, then you remove a second one again from the equatorial, and what do you get? You get a T shape. I think that one's pretty obvious. Probably don't need to look at that much more. Finally, you remove a third, and you come up on this linear shape. Okay? Alright, and then on to the octahedral. So the octahedral is, you might call it a square bipyramidal, right? Because you've got a pyramid on the top, a pyramid on the bottom, and you got the square in the center, but everybody's a square, right? If you remove one of the apexes of the bipyramidal, you come up with a square pyramid shape. Okay. Remove a second one, and you're to just a square, right? And so you could call that square planar. Okay. Those are really the only two important ones. So again, here's the square pyramidal shape. Here's the square planar shape. Okay. All right. So here's kind of a recap of everything that we've looked at. All right. So we started off with, if we've got two bonded groups, right, and no lone pairs, we've got linear geometry, right? If we have three bonded groups, okay, and one central atom, no lone pairs, we've got trigonal planar geometry. If we've got three total electron groups, two of them are bonded and one of them's a lone pair, we get the bent structure, okay? And then going through tetrahedral, we've got four electron groups, all four of those being bonded, you get the tetrahedral shape. You got, again, four electron groups, only three of them bonded, one lone pair, and you've got the trigonal pyramidal. Four, two bonded, two lone pairs, and you get the bent shape. Okay, so this kind of gives you the starting point. You could fill in the fives and the sixes. Okay, here's just a bunch of the different structures. All right, you got the linear, the trigonal planar, you got the bent, you got tetrahedral, you got trigonal pyramidal, trigonal bipyramidal, seesaw, octahedral, square planar. All right. Here's just the octahedral for one last look at the geometry, and I believe that's the last slide. We'll go into a lot more detail on moving forward into Okay, how does this really work? Because the Lewis dots theory that we've been looking at says valence, right? Valence shell electron pair repulsion. Yet we've got S's and P's as the valence. It doesn't make a lot of sense that we actually get into these types of structures, and so we're going to do something called hybridization next, and we'll hybridize these orbitals, and it should then quickly, you should be able to quickly move from these structures that you've built to this hybridization, and it should make a lot of sense. All right. This, here we go. Didn't come up to stop it yet, so you're probably still listening to my voice. I don't know how to stop it. How do I stop it? Stop recording. Maybe that will do it.